Hey guys, good afternoon all. My name is Ryan Kazanciyan. I'm a technical director with Mandiant. I'm here with Matt Hastings, one of our consultants. Both of us have done end-light incident response investigations at Mandiant for myself upwards of 5 years, for Matt upwards of 3 years? Yep. Yeah, so apologize if we sound a bit hoarse. I've been in Vegas since Friday of last week, teaching and presenting, so this is like the last little bit of my voice that's left, so hopefully it'll carry us through this hour. But thank you for coming. Really excited to share our research with you. So we're going to talk about investigating PowerShell attacks. To make sure we're in the right room here, this is PowerShell attacks, not that blue shell. So if that's what you're looking for, you're in the wrong presentation. But the reason that we did this research, so we continuously are seeing attackers adopt interestingly novel approaches to compromise and persist in environments. And we had seen an increasing use of PowerShell in some of the targeted attacks that we investigate starting about 18 months to 2 years ago. Very sporadic, nothing really consistent, nothing I would call a trend at the time. But earlier this year, Matt and I worked the case, again, targeted compromise of a Fortune 100 organization. We spent about 4 months investigating in this environment, and as it turns out, this victim's VPN space had been compromised for over 3 years. And attacker, of course, maintains domain administrator during most of that time, and so they kind of have free access to the majority of the environment. But the way that they conducted the majority of their command and control, at least while we were watching, was from their own originating attacker system through the VPN. They were targeting the victim workstations and servers using a combination of stuff we see very often, like scheduled tasks, and stuff that we had not seen quite so often, PowerShell remoting and copying and executing PowerShell scripts on the target systems. And this turned out to be forensically very challenging because you don't get to see what's on the attacker system. And when you conduct a lot of these attacks like PowerShell remoting over the network, it's very difficult to see what was actually done on the host on the endpoint side, especially if it's all in memory. So this led us down the path of doing some of this research, and that's why we're here today. We're not going to really go into a PowerShell 101 here because it's way beyond the scope of this talk. Suffice it to say that PowerShell is incredibly powerful. It is a command line and scripting environment in Windows that takes the functionality that you might see in batch scripts or VBS scripts or other types of scripts Windows has always supported and just ratchets it up a whole other level. So you can execute commands, you can interact with the Windows API, you can interact with the registry, and then you can do really cool stuff like access the entire .NET framework or reflectively load and execute DLLs in memory. And so this makes it very useful for system administrators and developers using PowerShell for legitimate purposes. But it also means that attackers can do some really neat stuff with it. And as a natural consequence of that, a number of developers have built some really cool penetration testing and attack frameworks that use PowerShell. PowerSploit is probably the best known, written by a number of guys, Chris Campbell, Joseph Bialik, Matt Graber, who works with us at Mandiant FireEye. And PowerSploit's awesome. So it does reconnaissance, it does remote code execution. It's got like a module called invoke Mimikatz that will take the Mimikatz code and in memory run it on a remote system without ever touching disk and do all the cool stuff Mimikatz does. And a lot of other modules. And then there's other tools like Metasploit has had PowerShell-based modules for a little over a year now. Veil PowerView, Nishang. More and more attack frameworks are integrating PowerShell into their toolkit. So we've got targeted attackers using it or learning how to use it, attack and testing tools using it. We're also seeing mass malware use PowerShell. The first PowerShell mass malware was actually shortly after the creation of PowerShell in 2006. It was called PowerWorm. It was kind of a proof of concept, didn't really do much. But now there is actual mass malware that uses PowerShell. Trend Labs has actually reported on a couple of samples within the last 12 months, one of which was like a classic ransomware sample that encrypted all your files and demanded payment. But the bottom line is, attackers of all disciplines are learning how to use this stuff. So instead of trying to come up with an investigation methodology that was specific to one type of attack framework or tool or malware sample, we wanted to take the lowest common denominator. So what are the fundamental ways you can use PowerShell to interact with a system? And then what forensic impact does that have? So the three scenarios we exercised were executing a PowerShell script on a local host, using the PowerShell remoting feature, which uses a protocol called WinRM, Windows Remote Management, to interact with the remote host. And then persistent PowerShell, which is simply taking some PowerShell code and configuring a system to automatically execute it upon login or boot time. And for each of those scenarios, we ran test cases to see what the impact was of the registry on the file system, on event logs, in memory, and then if you were monitoring the network traffic. A few assumptions. The first that we make is that the attacker has either local or domain administrator access to the target system. You may be thinking, well, isn't that cheating? But what we're dealing with when we look at this is post-compromise scenarios. So I don't care about the initial exploit vector. I care about now the attacker has a foothold in the environment and they're achieving whatever mission they have in that environment, meaning they're moving laterally from host to host, they're doing reconnaissance, they're looking for data to steal, they're stealing data, and they're doing whatever else brought them to that environment in the first place. And in almost every Windows environment we ever use, the attacker successfully gains administrator privileges very quickly. And so then the question becomes, how covertly can you conduct all those other stages of compromise without getting caught and kicked out? And PowerShell enables that quite nicely. So that's the context in which we're going to be looking at all of this findings. And then a quick version reference. There's a lot of different versions of PowerShell. I think 4.0 is current, 5.0 is in the works, but in most enterprise environments you're going to see 2.0 because that's what's installed by default on Windows 7, actually Vista and later, and Server 2008 R2. Windows 8 includes PowerShell 3 by default, Windows 8.1 includes 4, but we don't expect to see corporate environments really adopting either of those platforms for quite some time. So the downside of that is a lot of the cool things that are in PowerShell 3 that myself and Matt will talk about later won't be available by default and therefore won't be installed in most environments. You have to basically apply an optional update to the Windows management framework to gain access to later versions of PowerShell on those versions of Windows. So let's begin by talking about memory analysis because in some ways this is the worst case scenario, which is an attacker interacts with a targeted host, they use PowerShell remoting, and they don't write or touch disk at all on the target system. So worst case scenario because it's volatile, the session ends, you may come back to the system in minutes, hours, days, and based on a lot of factors, we wanted to understand what would be left behind assuming the system had not shut down or been rebooted, and how long could you find and recover that, and just how much could you get out of memory. So to understand this, we need to kind of understand the process hierarchy that PowerShell remoting uses. So what happens when myself as a client initiates PowerShell remoting to connect to a target system on that target system's memory. So the way it works is, let's say I use the PowerShell commandlet invoke commands to run evil.exe, and presumably evil.exe is already on the target system. svchost.exe, the service hosting process that is running the DCOM launch service, instantiates an instance of wsm-provhost.exe. And then that instance of wsm-provhost in turn executes evil.exe. So evil.exe's parent process will be wsm-provhost, and wsm-provhost's parent process will be that instance of svchost. In contrast, if I use PowerShell remoting to execute PowerShell native commands, in other words, just commandlets or code that is solely resident within PowerShell's language space, what actually happens is wsm-provhost spins up again, but you don't see a child process PowerShell.exe spawned by it. The PowerShell code runs within the context of that wsm-provhost process. So you don't see a child PowerShell process when you do remoting like this. So what's in memory? If you go to memory and you dump memory right when a PowerShell session, remoting session is occurring on the victim host, you can reconstruct almost complete command history from the wsm-provhost memory space. The problem with that is it terminates at the end of the session, meaning if I do one single PowerShell remoting command, the moment the command completes, that wsm-provhost terminates, and all that cool evidence in memory is totally gone. From a practical standpoint, that means that as an analyst or investigator, you almost never will get to the system in time to recover that process memory. So that kind of put us back to the drawing board to see where else in memory does any of this stuff hang out. And what we found is that another instance of the service hosting process that is running the Windows Remote Management Service, which is again what brokers PowerShell remoting, actually contains remnants of the SOAP objects that PowerShell input and output is marshaled into when you do remoting. And so we were actually able to find that this may persist after the end of a remoting session and even all the way up till reboot. We also found that bits and pieces of the same types of data could persist in the kernel and in the page file, but we suspect that that is probably just artifacts of paged pools in memory and therefore not something you could reliably expect to always find. So we're not going to read this in super detail, but we put together a table here of source of evidence in memory and how long you could find stuff after the fact on a system. And really your best bet is the WinRM instance of SVC host. If you dump memory from it, assuming the attacker is the only person that's interacting with the system through remoting, and assuming the system obviously hasn't rebooted, you actually can recover quite a bit of input and output from PowerShell sessions. And it looks like this, and I apologize if the colors are hard to read here, but here's an example of us running through remoting a PowerShell command that simply does echo test string PS session to this output file. And amidst this giant blob of ugly XML, you can actually see there is a RSP command tag and then the full command that we submitted in the command line. And we were able to recover that from memory many hours after that already had executed. A more interesting example is we use the PowerSploit invoke Mimikatz module, again through remoting. We actually use the technique where you download through PowerShell the script over the internet and then dynamically execute it, so absolutely nothing touches disk. This is solely in memory on the victim system. And again, we can see in the inset a complete command line of everything that was executed to pull and run the invoke Mimikatz PowerSploit module. So definitely possible to do this. Yes, this is painful. This is kind of like worst case scenario. You can recover evidence, but you're going to have to work for it. The biggest problem is that because we're looking at fragments of the SOAP and the PowerShell remoting protocol, XML objects that are used when you do remoting with the system, it's not like you've got these well-structured objects that are retained in memory because they're being actively used. You're seeing stuff in basically portions of memory that are no longer actively allocated to anything. And so the bottom line is you can do string searches looking for some of these tags that we have here, like RSP command line, to find these strings and hone in on the commands, but you're going to have to sift through a lot of garbage. So in summary, timing is kind of everything rather. That's always the case with memory analysis, but especially with this. Because there is no proper place at which in memory all of PowerShell history is just retained forever. It has to be reconstructed from what's left behind in the Windows RM memory space. And then things like system uptime and memory utilization all can impact how likely you are to recover these types of artifacts. So I'll hand it off to Matt to talk about event log analysis.
Thanks, Aaron. So for the event log analysis, we looked at a similar scenario that Ryan just talked about, where an attacker is interacting with the system remotely via PowerShell. But then we also looked at what happens if an attacker actually logs in and runs PowerShell locally. And for each of these scenarios, we try to answer three key questions. So which event logs specifically are capturing this activity? And this will be event logs that are directly writing PowerShell activity. So what you'll see in the next slide is event logs that PowerShell writes to directly, and it doesn't necessarily cover other event logs that may contain relevant forensic data. So for example, in the remoting example, an attacker logs in, you would expect to see the login be recorded in the security event log. That really wasn't covered in our research, but definitely another source of evidence. We're also looking for each event log that we're looking at what level of logging detail. So ideally get full command history on everything executed on the system, but in reality, what are we going to see there? And then specifically some of the differences between PowerShell 2 and PowerShell 3. So we identified 5 specific logs that may contain PowerShell commands or may contain some relevant information related to PowerShell execution. And in the next few slides, we'll walk through what happens in a local versus a remote scenario. So starting with the PowerShell event log itself, we identified 2 event IDs, 400 and 403, that contain some bits of relevant information. Again, not ideal if you're looking to fully parse back what was executed. But here in event ID 400, you're seeing that the event engine state changes from none to available, indicating that PowerShell started. So looking at the generated time of this event, you can say, okay, PowerShell was run on the system at this time. Corresponding to event ID 403, you can now see, okay, PowerShell is done running. So take those 2 times, and you can say roughly it ran between X and Y. The host name here, console host, indicates that it's a local session versus a remote, and we'll show you what a remote session looks like here in the following slide. The PowerShell operational slide and operational event log here in PowerShell 2.0 really doesn't contain any additional information that we found that's forensically significant. So we did find one EID that contains the same information that PowerShell console is starting up, but again, you can get that from the same event log we spoke about previously. In PowerShell 3.0 and greater, it does write verbose error messages. So here at EID 4100, we're seeing that a script failed to run, and we get the full path to the script. In a remoting session, if you're actually looking at the accessing system and it fails to access a remote host, that will actually be written here too. So you can get the host name and IP address of the system attempting to be accessed. For PowerShell analytic logging, for those of you not familiar, analytic logging is disabled by default and probably for good measure. It's really meant for debugging purposes and not for long-term event log retention. So we did enable it, and we did find that at least in PowerShell 3.0 it does contain relevant information. So you can actually see here in event ID 7937, the test.ps1 script was run. So we can see, okay, at least a PowerShell script was run. Also, if you run a native commandlet, that's also captured in the same event ID. And finally, a dropper ID. See, if you run that from the PowerShell console, that's going to be recorded here as well. Now, what you don't get from this is any commands or arguments passed to these scripts. So you kind of get like halfway there, and then you really just want to know, well, okay, well, how are these configured? And there's better ways in 3.0 to record this information, so the analytic logging in this case is probably not worth it. Moving on to the remoting section here, back to the PowerShell log, in EID 6, and this is on the accessing system, we can see that the WSMan session is starting. And looking at this, you can say, okay, well, from the system, a remote session was starting where we're connecting to another host. And those from you who may not be familiar, WSMan is the protocol used by WinRM, which is what PowerShell uses for remoting. And then on the access system, again, we have EIDs 400 and 403. And in this case, we just see the server remote host as the host name, which indicates that this was a remote session versus a local session. Since in the remoting situation you are using the WinRM service, events are written to the WinRM event log. Specifically here in event ID 169, you can identify who the user that logged into the system was if you don't have security event logs going back that far for some reason, and the security protocol that was used for authentication, so in this case NTLM. Similar to the PowerShell log, you can also see the time frame of remoting activity looking for the client requests for the create shell and the delete shell. So that's available in multiple different event logs. So now going back to the PowerShell analytic log, because as far as 2.0 is concerned, which Ryan mentioned is prevalent. That was the word So, okay, I got to pause. Yesterday at Black Hat, we gave the same talk, and I mispronounced prevalent twice during the talk, and I completely forgot what that word was. Okay, that was it. All right, back on track. So in the analytic log, at least in 2.0, it's your only way of really recording command or capturing command execution and responses. Now the problem is, and we'll get to this in another slide, is that the actual content is written in a hex encoded format, so just looking at the log itself doesn't give you any information. And in fact, what you'll find is that every piece of information, everything that's sent back and forth between the two hosts are recorded. So the initial protocol negotiation, all that's recorded in the log in a hex encoded format. So you really have to dig through if you want to find what was actually run. So here's an example of the event log. So here, an object was received. The actual command that we ran here was get child item C, which is just an ls on C. But again, it's in a hex encoded format, so you can't really tell what happened. So if we decode it, you can actually see here the XML that Ryan was referring to in here. Hopefully you can see it. The command get child item, is it a script? Nope, it's not. And then you can see the arguments passed, so the C. So you can see it's a C. Looking at the analytic log now for the response that's sent back, this is for a single response that's sent back to the requesting system. Now remember, in PowerShell, when you run a built-in commandlet, everything that comes back to you is in the form of an object. So each object that's returned from this command is written as a single event in the event log. So if you run this get child item, it will generate enough events in the event log to match the number of items within the C directory. So it generates a ton of events that you'd have to parse through individually to decode and then map back to what was actually run and what was responded. So again, in 2.0, it's just not practical to do this. But there are some other options that you can implement. For the first one that we'll go through is some of the profiles that PowerShell has. So PowerShell has multiple profile options where you can configure code to be run at any time that PowerShell locally starts up. Here we've given an example of the global profile, and one thing you can use is the built-in commandlet start transcript, which actually records command input and output and writes it out to a file of your choice, and you can even write it out to event log format if you prefer. We've also seen some companies put together some custom code that actually overwrites the default prompt so that anything typed in will actually just be spit out to a file. Now, some of the limitations here are, like I mentioned, this is only for local PowerShell execution. It doesn't do anything over remoting. And also, you can launch PowerShell by setting the no profile flag so that none of this code is run. So again, it's a solution. It's probably not the best answer in the world, but it is something that can help you out. Also, if you're using AppLocker, AppLocker has an option for logging and enforcing scripting rules. So if you even just set it to audit, you can see here, okay, a script was attempted to run at this time, and here's the path to it. So even if you're not enforcing these rules, this is another option for you if you're running AppLocker. Moving now to PowerShell 3.0, the best option that we found is module logging. And what module logging allows you to do is actually get that clear text specific command input and output written to an event log in clear text for anything that's being run through the shell, both locally and remotely. And we'll show you what some of these look like here in further slides. So here we actually ran a slightly more complex command than what we've done in the past. So here we said get child item of the C temp directory, let's recursively, but only filter back files with the .text extension, and then do basically a grep, which is select string in PowerShell for the term password. So the top item here, you'll see that we've captured the command being sent to the system, and you have all the arguments being parsed out and available in a nice clear format. And finally, at the bottom, you see the response where you can actually see the file that it hit on and the line where it found the file, found the hit. Now, this can be slightly problematic when you run a script, because each line in the script or each command in the script will generate its own PowerShell event. So we ran the invoke Mimikatz module within PowerSploit, and it actually ended up generating over 1,200 events in the event log. So a large number of events that we couldn't possibly parse through, but when we got to the actual response from Mimikatz, we found that it actually wrote the clear text Mimikatz output in the event log. So you can see all your password hashes here clearly written in the event log. And now to talk about persistence, give it back to Ryan.
Thanks. So for this last bit that we're going to focus on, we wanted to talk about the ways in which PowerShell code could be configured to automatically run on a system. And obviously attackers like persistence, because if you're doing something like installing a backdoor or a keystroke logger or a card data track or track data swipe recording tool, any case where you want something to continuously execute on a system and survive reboot, survive shutdown, you need to find some persistence mechanism. And this is very well understood in forensics and incident response. There's actually numerous techniques that Windows provides that are well documented, from registry auto start points like run keys, Windows services, things like recurring scheduled tasks, use of the startup folder. If you think about it, persisting PowerShell simply means making PowerShell.exe run with some argument to feed it a script. So all of these techniques are, like we said, very well understood, and we're actually not going to spend a whole lot of time talking about them because folks have done plenty of research on that in the past. But what we will spend a little more time on is persistence via Windows Management Interface, or WMI. And one of the reasons for that is the PowerSploit toolkit includes this as one of the mechanisms it can use to persist code of your choice. And so we thought that made it an interesting target. We also have seen attackers use WMI to persist not necessarily PowerShell, but other things like CScript or JScript, the other built-in scripting components in Windows that similarly are running built-in native Windows binaries to load and interpret code. WMI is very friendly for that sort of scenario. And to understand that, we need to briefly step back and explain how WMI works. And this is a big, ugly mess. I'm just going to give you a high level of it. Basically, it's this eventing infrastructure. So WMI has this notion of event filters, consumers, and then bindings between the two. So an event filter is basically a query that continuously runs against the state of the system, and when it's satisfied, it fires the consumer that's bound to the filter, and the consumer basically runs something. All of these things can be both set with PowerShell using the set WMI instance commandlet, and also, as we'll show you later, enumerated via PowerShell. So event filters. The event filter, as I said, is the thing that causes a consumer to trigger, and they're typically written in WQL, Windows Query Language. As a simple example here, these are both code snippets from PowerSploit. We have an example of WQL code at top that will fire when the system uptime is between 240 and 325 seconds. Basically a roundabout way of saying fire upon startup. The next one is an example where instead of a relative time, it says at 12 o'clock exactly, fire. So that will satisfy the filter. So two different ways to basically achieve the same thing, continuously run something on a predefined interval. The consumer is what runs when the filter is satisfied. In this example, of course, we're going to execute PowerShell. Now, the trick here is execute PowerShell to load what? Where does the evil code come from? You have a few options here. The thing that PowerSploit does by default is it puts the code in the system-wide or user profile. As Matt mentioned earlier, profiles load automatically when PowerShell executes. So if I create a persistence mechanism that simply runs PowerShell without any options, it loads the profile, and then by virtue of that, it loads the malicious code. So very simple technique, works very nicely. The other thing you can do is add your malicious PowerShell code to the arguments that you're supplying to PowerShell.exe and simply build it right into the consumer's command line. And in that case, you're only limited by the command line length limit that Windows enforces, which is something like 8,000 characters. That actually isn't too bad of a constraint, and in fact, the example up top shows that you can run compressed PowerShell code and have it decompress and execute on the fly, so you can fit a lot in 8,000 characters, certainly enough to do like first stage dropper type stuff. So how do you find this? There's really no good solution. The easiest solution to find malicious WMI filters in consumers that run evil PowerShell is through the use of PowerShell. The get WMI object commandlet lets you enumerate event filters, consumers, and the bindings between the two. We do investigations in a lot of large environments, so we've polled like 50,000, 100,000 node environments to get an idea of what's common and what's not in your average Active Directory environment. And what we've seen is that it is not common to have event consumers that execute PowerShell. That doesn't mean that in your environment it may not be legitimately used for some administration purposes, but the bottom line is you could baseline your environment very easily and determine what consumers and filter names and consumer names you legitimately have, and then look for anomalies. The other thing you can do is look at the file system of the host at which this occurred, but this is actually difficult because WMI is stored in the WBEM repository. It's this directory, C Windows System 32 WBEM repository. And the files that keep all of the WMI objects and event filters and consumers, namely objects.data is the key file, and it is this undocumented proprietary format for which there is no documentation whatsoever. Some of our reverse engineers have looked at it briefly and said that it's a big ball of hurt that they really don't feel like getting into. But the bottom line is that if you had a dead disk image, like forensically acquired, or if you just grabbed objects.data from a host, there's no good way to parse it and get back the intrinsic structure. You can do strings against it, which is kind of good. So strings will actually give you the event filter and consumer names. So if your attacker was foolish enough to create, my badass event filter, you would be able to string search and find that in objects.data. You also do get the command line. So if you do discover on a host that this technique is in use and the attacker is referencing PowerShell with a specific set of arguments, you can actually see that in strings in objects.data. If you're looking for things like, I'm examining a system, did these files get modified during a time frame of what I think is attacker activity? It's not going to work because Windows updates these files constantly. So it's not forensically significant if they change in a given period of time because they change all the time. Finally, you should definitely review all of the profile.ps1 files on a system that you suspect has been hit. Again, in most environments, you probably will just have an empty file. But it's so quick and easy to check the profile that you might as well look at it because, again, anything in the profile will automatically execute unless you supply the no profile argument to the PowerShell command line. So why not check it for malicious code? Finally, the registry. This was kind of disappointing. We, like many things in Windows, really hoped that creating a WMI filter or consumer would lead to some sort of change to the registry that could be forensically examined. And that really wasn't the case. The only exception was, depending on the filter that you use to create the condition that's going to fire your consumer, registry key might be created specific to the provider that satisfies that query. So the long and short of that is the example we had where PowerSploit uses a WQL filter that says run this on this exact hour and minute. It was like 12 o'clock in the example we had on screen. Creating that filter registers this key for Win32 clock provider. And by default, this does not exist in Windows environments. You have to create a WMI filter that uses that as its provider. And from all of the enterprise scale investigations we've done, I have not seen this key except when an attacker is using this technique. Now, of course, there's 100 million ways you could probably create WMI filters that don't use that specific provider, so this isn't meant to be comprehensive, but it was an interesting artifact of default behavior of PowerSploit itself. And then other sources of evidence. If you use the sysinternals tools, which are fantastic, autoruns was recently updated about a month or two ago. Version 12 actually will enumerate and display all of your WMI filters and consumers in a very easy to read format. So I definitely suggest checking that out. In memory, we didn't spend a terrible amount of time examining this, but that was mainly because the memory space of the WMI relevant processes are really, really noisy, and we didn't find any good, reliable way to recover evidence after the fact. Event logs do have some WMI stuff, so you can enable WMI trace logging, and then if an attacker registered a malicious WMI event filter in consumer, it would generate an event, but Windows also does this stuff behind the scenes constantly. So that one event is going to be buried among thousands of events generated during normal system uptime and probably roll off the log pretty quickly.
So just kind of to wrap some things up, we definitely didn't cover every single source of evidence that's available on a single host or even across the environment. We have released a white paper that's actually now public, at least in a draft format, and the final version should be out next week. And that has a lot more detail into some of our research and some of our findings. But just a few other places that you could look if all the other ones that we've gone through have turned up nothing. If you're looking at a Windows workstation and there's a PowerShell prefetch file created, that can certainly contains information on either if a PowerShell script was run or if during that PowerShell activity certain files were accessed that may be of interest to you. Now the only caveat here is that's only for local execution of PowerShell. Again, no remoting here. Also, there's a single registry key that normally I wouldn't say is going to be relevant, and it's the execution policy setting. So by default, PowerShell doesn't let you execute unsigned scripts, and that's just to prevent people from double-clicking bad scripts. But again, just like everything else in PowerShell, you can bypass it on the command line with the execution bypass flag. Now, in one situation, Ryan actually saw on one single system, the attacker modified this registry key to allow them to run unsigned scripts rather than just bypassing it on the command line. I don't know if they were just lazy and they were tired of doing it, but they did modify this key. Network traffic analysis, since PowerShell uses the WinRM service, looking at the WinRM ports, so port 5985 and 5986 use HTTP and HTTPS respectively. Now the payload for PowerShell is always encrypted regardless if it's HTTP, but if you are using HTTP in your environment, you can actually pick up header information which contains the PowerShell version. So in that case that we've been mentioned previously, the attacker is actually using a different version of PowerShell than what they use natively in the environment. So they actually wrote they actually did some network monitoring and were able to detect when the attacker was using PowerShell based on the version in the headers.
And the NetFlow stuff.
Yeah, and then looking for anomalous net flow. And then we'll get into a little bit more of that here on the next slide. So really the lessons learned and what we'd recommend most companies do is they upgrade and enable module logging if possible. So moving to PowerShell version 3 or later and implementing module logging was really the best solution that we found in all of our research. Beyond that and kind of looking at a higher level, baselining legitimate PowerShell usage in your network can be key in identifying anomalous or malicious PowerShell usage. So what is the execution policy setting, and then does it ever change, and if so, why is it changing? How do you name your PowerShell scripts and where do you put them? And then looking for other directories that may not match your either path or naming convention. Do you use remoting? Is remoting enabled by default, or is it only enabled on certain systems? And then baselining that usage. What users use remoting, and from what subnets are they doing it from? So is it only your admins? Is it only server admins? And do they always work from a similar subnet? And then baselining all of that to say, okay, this is what good PowerShell looks like in my environment, and then looking for anomalies through the methods that we described previously.
Yeah, the bottom line is that with the exception of module logging, there is no perfect solution that we found for PowerShell forensics, which is why attackers are going to continue to do it. So like Matt said, Taking that step in advance before you have an incident to understand how it's being used in your environment can save you a lot of legwork in the future when you may actually have to respond. The thing we often find is that during your investigative process, PowerShell isn't the initial lead you get, it's some other artifacts of activity on the system. And as you do your forensics and timeline analysis and see some of these things that we presented today, you might now get an indication that the attacker was using PowerShell, whereas if you didn't know to look in these event log entries or in these places in memory, you might completely miss that that's part of their toolkit. And therefore, they might be able to successfully use it without being detected in post-compromise stage of activity. We want to acknowledge a number of folks that helped us out. Matt Graber, who works with us at Mandiant, co-author of PowerSploit, has done a lot of cool work on attack research with PowerShell, as has Joseph Bialik, Chris Campbell. A lot of folks at Microsoft have also reached out to help us out, especially I want to thank Lee Holmes. The folks at Microsoft are keenly aware of attackers using PowerShell. It's a difficult situation when this is all under the context of an attacker who already is an administrator on a system. Obviously, all bets are off from a security standpoint when that happens. So they are definitely working to make it more audit-friendly and easier to monitor. And I've been told that there will be some cool stuff coming down the pipe to make it easier for those who are running it in their environments. So I think good things are going to come out of this. But once again, thank you for your time and attendance here. If you have any questions, it looks like we have a couple of minutes, so please step up to the microphone and we'd be glad to answer them. If you want to talk to us directly, you can either catch us after the talk or email us or hit us up on Twitter. But at this point, we'll stop for any questions. Sure. Could you just go up to the mic, please, so that it gets caught in the recordings?
Oh, all right. Well, then just speak loud, and we'll just repeat it.
Do you recommend definitely upgrading to at least PowerShell version 3? Are there any major advantages to upgrading all the way to 4?
The question was, we recommend upgrading to PowerShell 3. Is there any reason we could just not update the 4? Not that I know of. I think you could just as well update the 4. The reason they don't actually make it an automatic update is that there are a couple of things that were deprecated between 2 and 3. They're exceptionally minor, but for like the very small pool of people that are using PowerShell for like sysadmin or exchange management, you may not want to break things, right? So I would check whether the things that you use in 2.0 are not broken by 3, but 2 to 3 was the major change. So does that answer your question?
Yes, definitely.
Awesome. Any other questions? All right. Well, once again, if you want to talk to any of us directly, we'll be here, or you can just reach out to us via email. But thanks once again. You guys were great. Appreciate having us here.